Taylor series. Objectives. By the end of this lesson, you should be able to recite the Taylor series for sine x, cosine x, e to the x, arctangent x, and 1 over 1 minus x, and then use the known Taylor series to evaluate limits, derivatives, integrals, and find other Taylor series. Alright, so here are some Taylor series you need to know, and they're going to look really familiar because they are exactly the Taylor polynomials except that they are series, so they go on forever. So the Taylor series for e to the x, so e to the x is exactly 1 plus x squared over 2 factorial and so on. So the general term is x to the n over n factorial, but this is a series, so this goes on forever. So the only difference between the series and the polynomial is that the series is infinite. It goes on forever. So sine x is exactly x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So that pattern is they're going to alternate, and for sine x, all the degrees have to be odd degrees over their respective factorials. For cosine, cosine is exactly 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial and so on, where for cosine, each of the exponents have to be even. Arctangent is x minus x cubed over 3 plus x to the 5th over 5 and so on, where it's almost the same as the sine one, except that there are not factorials in the denominator, just the individual numbers. And then finally, 1 over 1 minus x is 1 plus x squared plus dot 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 up to x to the n, and it goes on forever. So these are Taylor series you need to know, but it's really just the Taylor polynomials with the ellipses that indicates that this goes on and on forever, and these are exactly representative of each of their respective functions. Alright, so here we want to compute the limit as x approaches 0 of sine x over x using the Maclaurin polynomial. So we should already know that this limit equals 1, so this is one of those trig limits that was just given to us that we needed to memorize, but now we can actually prove this using Maclaurin polynomials. So Maclaurin is in because the sine function is centered at 0. So here, let's go ahead and rewrite the numerator using the Taylor series expansion. So sine x over x is going to be the limit as x approaches 0. So the sine function starts with x, and then it's minus x cubed over 3 factorial, which is 6, plus x to the 5th over 5 factorial, which is 120, minus and so on and so forth, divided by x. So now let's go ahead and simplify this. This is the limit as x approaches 0. Well, there's only one thing on the bottom, so each thing on the top goes over that one thing on the bottom. So this is like x over x minus, and then I have, this is like 1/6 x cubed over x plus 1 over 120 x to the 5th over x, and so on. So now this is the limit as x approaches 0 of 1, x over x is 1, minus 1/6 x squared. So the x cubed over x will reduce down to x squared, plus 1 over 120 x to the 4th, and so on. So now, as x approaches 0, we can use direct substitution. So if I substitute 0 in for every x, which will be in every term except for the first one, all of these pieces are going to end up being 0. So in other words, I'm going to have, so the limit will be gone here. This is just going to be 1 minus 1/6 times 0 squared plus 1 over 120 times 0 to the 4th plus a bunch of zeros. So the final answer is just going to be 1, as we already knew that it was, but now we were able to prove that the limit as x approaches 0 of sine x over x is 1 using the Taylor series expansion for sine x. Alright, now let's show that the derivative of sine x is cosine x using Maclaurin polynomials. So let's start out with the derivative of sine x, which is the derivative with respect to x of the expansion x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. So now let's apply the derivative. Since we're doing all these terms are being added and subtracted, we could do each one separately. So the derivative of x is just 1. And now the derivative of x cubed. So remember, 3 factorial is like 1 over 3 factorial. So let's put that in the front. So I have 1 over 3 factorial in the front. The derivative of 3x, or x cubed, is 3x squared. And then plus 1 over 5 factorial. The derivative of x to the 5th is 5x to the 4th. And we'll go one more, minus 1 over 7 factorial. The derivative of x to the 7th is 7x to the 6th. And so on and so forth. So this is 1 minus. Alright, so here's 3 factorial, but there's a 3 on top. So 3 factorial, which is like 3 times 2 times 1. So if I cancel the 3 on top with this 3 on the bottom, then what I have left is x squared over 2 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. So this 5 on the top will cancel with this 5. So what I have left in the denominator is a 4 factorial, and on the top I have x to the 4th. So now hopefully you can see the pattern that this 7 factorial will turn into a 6 factorial because the 7's will cancel, and then I have my x to the 6th on the top. So there's my alternating representation of the cosine Taylor series. So the derivative of sine we just showed using Maclaurin polynomials, or Maclaurin series, Taylor series, is exactly cosine x. So that's probably what that should have said, using a Maclaurin series or a Taylor series.